This week's lecture is going to be the beginning of our basic electronics section, and we will talk about some definitions, and then we'll talk about Ohm's law, and we will discuss some different components. To start with, in the definitions section, we're going to look at a word called voltage, which was originally found by Alessandro Volta, and he was Italian. And voltage is what makes electrical charges move. It's the push that causes charges to move in a wire or other electrical conductor. It can be thought of as the force that pushes the charges, but it is not a force in and of itself. Voltage can cause charges to move, and since the moving charge is a current, voltages cause current to flow. The voltage is an electrical potential difference between two places, and in many cases that's the two plates within a battery. There are two types of voltage that we will deal with. One is called direct current, and the other one is alternating current. Now, interestingly enough, the word current is used in both of those terms, but that is a definition of the type of voltage, push or pressure, that is being exerted on the electrons. The second term we're going to look at is current. Current is the actual flow of the electric charge. When a voltage is placed on a wire or other conductive material, the electrons respond by moving. When a current is flowing, it accelerates when there is no resistance in the circuit. And you can think of current as the rate of electrical flow over time. The third term we're going to look at is resistance, and this was defined by George Ohm, and therefore has his name as the unit of measurement. And the electrical resistance of an electrical conductor is the measure of the difficulty of passing an electric current through a substance. As the resistance increases, less electricity will flow through the circuit. And George was the first person to quantify resistance as a ratio between voltage and current. The equation that he came up with is resistance equals voltage divided by current. Power is what we normally hear of or talk about in watts, and that was defined by James Watt. And electrical power is the power dissipated by an electric circuit. Electric power is a measurement of the rate at which the energy is used over a period of time. So power and current are very closely related. And if you think about it, we have circuit breakers in our houses or our apartments that are rated in amps, which is current, but yet when we plug an electric light bulb in or a toaster, those devices are most often measured in watts, because power or wattage is the dissipated electricity that occurs when current flows through a wire that is pushed by a voltage. So when an electric current flows through a circuit, it is slowed down by the resistance of the circuit. The devices that convert the current into useful forms of work, such as heat radiation in that toaster, or light emission in a light bulb, or mechanical motion in a motor, or acoustical vibrations in a speaker. Inductance is a passive component designed to resist changes in current, and inductors are often referred to as AC resistors. The ability to resist changes in current and store energy in its magnetic field is its main use. And the property of a circuit element, which tends to oppose any change in the current flowing through it, the inductor or the inductance for a given inductor is influenced by the core material, the core shape and size, the number of turns in the count of electrical wire wrapped around the coil or the core, and the shape of the coil itself. And most inductors have their inductances expressed in microhenries. And Joseph Henry, of course, was the guy that invented that. The next thing we talk about is capacitance. And the capacitors have the ability, or think of capacity, to store electric charges. Similar to a battery, but much smaller in size, weight, and capacities. A battery can store a charge for a considerably long amount of time and a considerably large amount of charge. Capacitors are basically two metal plates separated by some type of insulating material so they can't touch each other. And when a current is passed through the circuit with a capacitor, the plates charge. One of them charges positively, the other one charges negatively. And they come in many sizes, and the capacitor-like effect, it can also result from two conductors being in close proximity, two pieces of wire, for example. And now let's talk about an electrical conductor. An electrical conductor is any material which electricity, heat, or sound can flow through. An electrical conductor conducts electricity, and most metals, like iron and copper, are electrical conductors. These materials are commonly used to make wires that carry electrical current. Gold-plated connectors are common because of its low electrical resistance and the fact that the gold does not oxidize. Oxidization is usually exhibited in corrosion, which is when that penny that you keep in your pocket turns from nice and shiny to that dull brown color, or rust, which you see when iron objects are left outside for an extended period of time. Semiconductors, on the other hand, allow the flow of electricity conditionally or part of the time. Resistors resist the flow of electricity by converting some of the energy of the electricity or the current into heat. Insulators, on the other hand, such as glass or plastic or rubber, stop the flow of electricity. And some materials, when they're extremely cold, are considered superconductors. Now, we talked earlier about direct current and alternating current. Direct current, or continuous current, is the flow of electricity in a single direction from the positive to the negative in a conventional current thought process. The current always flows in the same direction. Batteries are an example of DC power, and the first commercial electric power transmission system that used DC was developed by Thomas Edison in the late 19th century. Now, I'd mentioned earlier that the electricity flows from positive to negative, and we call that conventional current. We owe that to Ben Franklin. He did not know about electrons when he defined what electrical flow was, so he assumed that electricity flows from positive to negative, so that is conventionally how we talk about it. But in reality, the electricity actually flows from negative to positive. For all intents and purposes in this class, though, we will be looking at conventional current because that's what's practiced in the United States. Alternating current, on the other hand, is a current that alternates in its magnitude and its direction. The direction of the current flow is constantly being reversed. The usual waveform of an AC power circuit is a sine wave due to the efficiency. So audio is also an example of alternating current when we're talking about audio signals in wires. Nikola Tesla experimented with electrical resonance, the induction motor, and new types of generators and transformers, and he came up with the first system of alternating power transmission, alternating current power transmission. Now, DC power was used here in the United States and in Europe in the early days, but DC was very inefficient and it was very dangerous to transport from one location to another, say from a generating station to the end user. AC used smaller wires and was much more stable and wasn't as dangerous for people and people in houses and people working with it in the electric factories. So now we're going to kind of tie a few of these things together in a section called Ohm's Law. So for this, I'm going to drag my little whiteboard over and put it here. So basically what we're going to start out with is, if we remember, we talked about voltage being the potential of electrical to flow. So to demonstrate this, we're going to start out with a column that is full of water, and the column is closed at the bottom. So up above here is an infinite amount of additional water, but what we're going to be concentrating on is just the water in this column for the moment. So the voltage potential is the pressure being pushed down on the water in this column. So voltage is electrical potential or electrical pressure. Electrical potential. So the second term that we were introduced to was the current. And current is with the symbol I. Voltage, remember, had the symbol of V. Current is the measurement of how much voltage is flowing. So to demonstrate this, we're going to put a sensor, let's say right here in the middle of this tube, and the sensor is going to measure how much water passes. Some of these spots on this tablet don't work so much. How much water passes through this spot? I think I might be pressing too hard. Okay, so how much water passes? Okay. And then the third thing that we talked about earlier was resistance. Not doing well with this pen for some reason. So resistance is how the voltage is impeded or slowed down as it travels through. So looking at our diagram here, if we were to open a flap on the bottom of this tube, then the water starts flowing out. And as the water flows, we measure how much water is passing through this point at any given moment. That represents the current. Resistance is the slowing down or the impeding of the flow. So if we replace this tube with a tube that gets very narrow in the middle, we end up with, this is our point of resistance. And now with that same measurement tool up here, the amount of water passing through this area at the top is going to be much less per unit time because of the restriction imposed by the narrower tube here. So this is a water representation of what the voltage, current, and resistance, how they're related to each other. And now to look at this in terms of an electrical diagram, if we start out, let's draw a battery. So we have a battery over here, and even though this looks like one of those little tiny 1.5 volt batteries, let's assume it doesn't want me to draw a circle. Let's assume that this battery is a 12 volt battery. And if we have a wire coming off the plus side of the battery, now remember we're talking conventional current, that wire is going to go to something that is called a resistor. So for right now, we'll just draw that as a rectangular box. And this is some kind of resistance. And then the current continues to flow back to the other side of the battery. Now, if this resistive element is a light bulb, we would draw it like a circle or a loop with a circle around it. And if we put this in place of the rectangle, we basically have a flashlight. If instead we put a strip of wire, and we'll represent that by a squiggly line, the strip of wire might be the little wires inside your toaster. And when you turn your toaster on, those wires start glowing, because in the first case, the voltage and the current flow is converted to light that comes out of the light bulb. In the second case, it's converted to heat that comes out of those heating coils. So the relationship of these is, if we have a 12-volt battery, so V is equal to 12, and we know that the equation is V equals IR. So if we know the resistance, for sake of this example, let's say the resistance, or R, is also 12 ohms. If we solve this equation now for I, what we're going to do is divide both sides by R, and then the R on the right side cancels out, so we have voltage divided by resistance is equal to the current. So in this case, the voltage is equal to 12, and the resistance is also equal to 12, so the current is 1 amp. So I is equal to 1 amp. So as you can see, the higher the resistance, the number on the bottom gets larger and the current flow drops. So if the resistance were 120 ohms instead of 12 ohms, you would still have 12 volts on top, and you would have 120 ohms, and that the symbol for ohm is the omega symbol. So that should be an omega symbol, but the pen didn't draw it right. Let's try erasing this. We'll try again. So we have 120 on the bottom, and then the ohm symbol. So at this point, the current is only 0.1 amps. Because 12 divided by 120 is 0.1. So this is a very simple explanation of Ohm's law and how voltage, current, and resistance are related. So as the resistance increases, the current flow, the amount of electricity flowing through the circuit, decreases. So resistance increases, the path gets narrower, more of the current is not allowed to pass through, but it is most often converted to heat. It is not just less current passing, the leftover current is converted to heat. Now we will go back to the presentation and we will look at a few more slides related to Ohm's law. If you look on the internet, you will find a bunch of pictures that look like this, or you can copy it from the PowerPoint that I will provide. This gives you all of the equations related to voltage, current, and resistance, and power, which we really haven't talked a lot about power yet. But if you look at the upper right corner, if you know the resistance and the current, that's the R times I, you will be able to calculate the voltage. In the lower right corner, if you know the voltage and the current, the V divided by I, that will give you the resistance. In the lower left corner, if you look at if you know the voltage and the resistance, it's voltage divided by resistance gives you the current. Those are kind of the three things that we've talked about so far, but this particular diagram gives you all of the different equations that will be necessary to do any kind of calculations in the audio field and on any of my exams or quizzes. So having this chart will be very helpful, and the most you need to know is how to square something and how to do a square root, and I will have very few of the square root things on the exam because you almost never need a voltage if you have a power and a resistance. Another way to look at Ohm's law, which makes it a little bit more obvious, is if you arrange them in a triangle with the V on the top and the I and the R below it. If you look at the first triangle, to calculate the voltage, you multiply I times R, and that can be signified by the two of them being side by side. If you know the current, the middle triangle, then if you need to know the current, you can divide the voltage by the resistor because the V is above the R. And if you know the voltage and the current, you can divide the voltage by the current to give you the resistance. So this is a very helpful diagram as well. And then one more, which we haven't really talked about yet, is the relationship of the voltage, the power, and the current. And that triangle would look like this. And again, we'll talk more about this in the next lecture. So for the exams and the quizzes, make a copy of this and make a copy of these two pages here. The remainder of the lecture today is going to talk about what some of these components that voltage, current, and resistance affect or are affected by. We'll talk about just looking at those components. And the first one is pretty obvious. It's wire. And wire comes in a lot of different shapes. In the left side, that would be probably typically speaker wire because you have one colored and one clear jacket on the two strands. And the red and black one is typically power. The multi-conductors are used for a lot of different things. And if you look at the red and white one in the upper right corner and the white and black one in the lower right corner, those are typically the kind of cables that you're going to see in the audio industry, where you have two signal carrying wires and then a braided shield, which can either be a braided copper shield or it can be braided steel with foil around it as well. So those are different types of wires. And when you have multiple wires in one outer jacket, the whole thing is typically called a cable. And the resistance of the wire depends on its size or diameter and its length. The larger the size, the lower the resistance. The longer the length, the higher the resistance. So when you have a piece of wire that has to carry a large amount of current over a long distance, you need to increase the size of the wire, each of the individual conductors, to compensate for the length of the run. The next component, which you've seen if you've looked at circuit boards or seen pictures on the internet, is a resistor. And a resistor is typically a tiny cylinder. They come in multiple different sizes, and they usually have colored bands on them, and the colored bands tell what the resistance value is, because sometimes the components are really small and you can't write on them, so it's easier to put colored stripes around them. In the upper right-hand corner, you see two versions of how a resistor is drawn in a schematic. In the United States, we typically draw the squiggly line called here R1, and the 1 K ohm stands for 1,000, K meaning kilo, ohm value. On the right, the international symbol for resistor is typically a rectangular box, and this particular resistor has a value of 230 ohms. The two resistors on the bottom are variable resistors, and think of those as like a volume control. When you turn it to the right, it gets louder. Turn it to the left, it gets quieter. And that's because there's a slider that slides along the resistive material, changing the amount of resistance between any of the two pins, the slider and either end. And if you look on the left-hand side of the picture, you can see a potentiometer. It's the thing with the round cylinder with the silver thing sticking out of the top, and you can see the three wires on the left-hand side. The next thing we'll talk about is ground. And ground is very important in audio engineering and in just electrical work in general, because it's what keeps your signal usually balanced, and it allows you to deflect any external noise from getting into the wires. If you remember in the previous picture, two pictures back, the braided shield in the microphone or audio cables on the right is usually connected to ground, and it allows the cable to reject some of the external noise, giving you a nice quiet signal. Grounds are also found outside your house. It's a metal rod that is usually next to the electrical box that is pounded into the ground, usually about 8 or 10 feet. And it's the way that your house is protected from people getting electrocuted. We talked earlier about batteries. Batteries come in multiple different shapes and sizes and multiple different voltages. In the upper right corner of this picture, you can see the diagram or schematic diagram for a battery, and it's usually alternating long and short lines in parallel to each other with wires connected to the outside edge. Sometimes you'll see a circle with a plus and a minus. That indicates a DC power supply, and a circle with a sine wave in it represents an AC power supply. And of course, on the left, you can see a bunch of different batteries that provide power. And on the right, you can see a bunch of devices that plug in to your electrical outlet that provide power. The next thing we'll look at is a light bulb or a light emitting diode. Two totally different objects that perform similar purposes. On the left, you can see the typical light bulb. And the light bulb is that coil of wire that's just connected to a battery or an AC power source. And it is literally a resistor that lights up really brightly. And therefore, because it lights up so bright, they typically have very low resistance. And that's what allows them to light up or heat up. And another example of a light bulb, kinda, is that heating coil in your toaster. That's, in essence, a light bulb that doesn't give off as much light as it gives off heat. But notice light bulbs get hot, toasters get hot. A light-emitting diode, on the other hand, is a semiconductor device. When electricity is passed one direction through it, it does not light up, but when you reverse the direction of the current, it lights up. And light-emitting diodes come in multiple colors, and you can also have multiple light-emitting diodes in one container, and those are usually your RGB multicolor LEDs. The next component is a switch, and switches are pretty simple. They just break the current flow by opening the circuit. And you can see a typical light switch in your house on the left-hand side, and then in the middle of the screen, you can see a switch switching back and forth. When the switch is switched to the left, the current flows through pins 1 and 2, and when the switch is flipped to the right, the current flows between pins 2 and 3. And the electrical schematic diagram of that switch is in the upper right-hand corner. You can see the common is the number 2 pin, and A and B would be the equivalent of the 1 and the 3 pins. The next component we're going to talk about is the transformer. And this is one of those things we talked about early on. An inductor you basically have a magnetic core of some sort, and we're primarily looking at the picture on the left now, and that core has 2 or more coils of wire wrapped around it. And when you put an AC current into one of the coils, it causes a magnetic flux to flow in the magnetic material, and it causes a current flow on the other side or the other coil of the transformer. And typically those black boxes that you plug in the wall for your cell phone or whatever, those contain a transformer. And on the left-hand side, it has a certain number of coils around it. And then on the right-hand side, it has a different number. And that can be seen in the picture on the right-hand side of this diagram. So if you had say 100 windings on the left side and you plugged 120 volts into it, and then you had 10 windings on the right, you would step the voltage from 120, where the 100 windings are, down to 12 volts, where the 10 windings are. So transformers are used to change the voltage between 2 different parts of a circuit. And in the case of the 120 to 12 volts, that would be a step down transformer, and you're going to have a 10-to-1 ratio on the windings. And transformers only work with AC, not DC current. The loudspeaker is another version of the inductor. And if you remember from the previous slide, we had a magnetic material with 2 coils of wire wrapped around it. In the speaker, we have a magnetic material with 1 coil of wire wrapped around it, and the coil is attached to the cone part of the speaker. And when a voltage is passed through the coil, it causes the coil to move up and down in the magnetic field, and that causes the speaker to move in and out, which is how we hear sound. And we'll talk more about this later on in the course. The opposite of the speaker is the microphone, and the microphone is in essence identical to the speaker. It is a magnetic center with a coil of wire and a diaphragm as opposed to a cone. And the diaphragm vibrates when sound hits it, causing the coil of wire to move within the magnetic field of the magnet, generating a very, very tiny small current in the coil, which is then picked up and amplified by the audio equipment. And that's how a microphone converts sound waves, the vibrations through the air, into electrical current, and then the electrical current ultimately is transferred back to sound waves through the loudspeaker. But as I said, though, the microphone creates a very, very, very small voltage when the sound pressure wave hits it. So we need an amplifier to amplify that very small voltage and make it larger so it can power a speaker. And in the center of this slide is the symbol typically that we'll use for an amplifier in a schematic. Amplifiers come in multiple different sizes, multiple different shapes, and for multiple different purposes. And this concludes this week's PowerPoint. So remember to go back and review the definitions at the beginning and make copies of the Ohm's Law diagrams, the circle and the triangles. And we will be talking more about Ohm's Law in the next lecture. And then we'll be talking more about some of the equipment and how it works in future lectures.